see, maybe this is that better?
Yes, it's better. Yeah, thank you.
Okay. It's always a little bit difficult because you don't see what you. I do not see what you see. So there's clearly.
Well, it seems like if you would like to see what we see, so it's better to use two.
Yes.
Two computers or.
Yeah. You have to have a second device. I have my iPad here, so I could do that, but yeah. So, but if it's fine, then it's fine. Just try it again. Maybe this is even better. Is that even better?
Yeah.
Okay. Let's see.
Well, I think that we can start. So, and it's my pleasure to introduce Professor Ronnie Ramlau from Radon Institute of Computational and Applied Mathematics. Well, Professor Ramlau, please.
Yes, thanks for inviting me. Thanks for having me. It has been a very interesting year in some sense, of course. At least compared to last year, we could have at least some talks at least in person. So this one is again, so we closed the year as we actually started it with some online meeting. That's of course the second best, but it would be nice to talk to you all. Maybe one thing, so at least for us, it's now a good time again, because today the current lockdown in Austria ended. So we can actually go out for having a drink, going to a coffee shop again. So this is kind of nice. So we will use that later this afternoon. Okay, but to my talk now. I'm going to talk a little bit about regularized recycling methods for inverse problems, and also considering some application. And this is joint work with my colleagues Kirk Sudhalter, who is currently in Dublin as a professor at the college there, and Victoria Hutterer, who's at my institute, but currently also on maternity leave. So everything has been done in a framework of our special research area, tomography across the scales, which actually closes the first 4 years and was recently granted an extension for another 4 years. Okay, so just a few words about regularization of ill-posed problems. What we are going to do here is, well, at least for inverse problems, as always, we consider a problem of the type Tx equals y. So T is here in this setting a linear operator mapping between two Hilbert spaces X and Y. And as in inverse problems quite often is the case, we assume we have only noisy data, so an approximation of the real data available that fulfills an error bound like this one here. So we have the norm of y delta, the data that we have available minus y is bounded by delta. And of course, everybody who deals in inverse problems knows that if the operator T is ill-posed, then we have to use regularization methods. Examples, of course, classical examples for ill-posed problems are computerized tomography. What I'm working also on is atmospheric tomography. It's when you do a kind of tomography of the atmosphere in order to reconstruct turbulences in the atmosphere. Related to that is also wavefront reconstruction. So if you have some kind of sensor that measures something and you do want to have a reconstruction, then you have to use inverse problems. Deconvolution, of course, is a very standard case of inverse problems. Okay, so why doesn't Oh, no. Okay. So what is the regularization method? Of course, everybody who is familiar with inverse problems knows that. So a regularization method is an operator or family of operators R alpha. So we have here a real parameter that maps from the image space Y to the original space X. And this is called a regularization for an operator T. If we actually have for any right-hand side Y delta that actually fulfills the noise bound here, we have a parameter choice rule alpha, and alpha may depend also on the data that maps here. This is so that's why we have here Y. And if we actually take the limit for the data error going to 0, apply R alpha of delta to the noisy data, then this limit actually should go converge to the true solution. So examples, of course, for that are Tikhonov regularization, Landweber iteration, conjugate gradient, and the classical parameter choice rule might be the discrepancy principle. So that's very classic. That's very well known for, I would always say, almost 100 years. But of course, since Tikhonov and others before. So since the 60s of the last century, I would say. Okay, so in order to get better reconstructions as you will get from a standard reconstruction method, it always makes sense to use additional information on the solution. Therefore, if you use that, the reconstruction, but also the stability of the reconstruction may benefit from that. So what are possible information we could use? Well, of course, we could use some information on the smoothness of the solution. For instance, if we do computerized tomography, we know that, well, at least on a larger scale, if we actually scan a human body, it's at least piecewise constant if you reconstruct density. Not piecewise constant, piecewise continuous if we actually want to reconstruct the density distribution. So we use Tikhonov regularization, we could use a proper regularization space that actually can be incorporated here in the penalty term. So it could be a Sobolev norm, for instance. Of course, what has always been done is, in particular, if we have several solutions, you use an available guess for the solution. And the classical case for that would be if you have something already reconstructed, if you have an iterated method, you use a warm restart of the iteration. In this sense, you're already quite close. Now, another way would be that you use a shifted penalty in Tikhonov regularization. So you put your information on the solution, that would be X0, your a priori guess, you put in the penalty term. Also, what has been very famous in the last couple of years, almost since a decade, I would say, you use structural information on the solution, in particular sparsity. So if you know, for instance, that your solution is sparse, then you could incorporate like sparsity constraints in your construction. So what we want to do is the following. We would actually look at methods that actually use the information that at least part of the solution belongs to usually a finite dimensional subspace U. So that's what we would like to look into. And this is actually something which has been or is very popular in numerical linear algebra, but it didn't actually move towards inverse problems. So what is it all based off? It's called augmentation via constraints over pairs of spaces. And it's based on the observation that iterative methods often compute the current approximation xj of the iteration by minimizing some functional over a finite dimensional subspace, calling here now Vj. And most prominent, of course, that would be Krylov methods that are used for Krylov spaces. So we have this well-known proposition here. If you look at the CG method, the method of conjugate gradients, if you actually have the J plus first iterate produced by the method of CG applied to the normal equations, which are associated to our operator equation Tx equal y, so normal equation because we need symmetric operators, then this iterate xj plus 1 can be formulated as we select this xj plus 1 belonging to a Krylov space kj plus 1, depending on t star t and t star y. So here you see actually how this space is formed. You take the span of t star y, t star t, t star y, and so on up to t star t power j, t star y. So that's the Krylov space. And you use xj plus 1 in such a way that the residual here, so y minus txj plus 1, is perpendicular to every element of the Krylov space when we actually apply t. So it's basically an optimization procedure that you have to do. Of course, in CG, we have an explicit way of doing that, but nevertheless, it's a characterization of the xj plus first iterate that it actually belongs to this space and fulfills this condition here. So augmentation now actually changes this approach. Well, what we want to say here is, well, we actually now take an augmentation space Sj, which actually consists of one fixed space U plus some Vj, and that's a space which could be associated to the Krylov space. And we also have some residual constraint spaces Sj tilde, which is U tilde plus Vj tilde. And in most applications, this is simply applying T to the spaces U and Vj. So in our applications, always like that U and U tilde have fixed dimensions K, so it's a finite dimensional space, and these Vj and Vj tilde are generated iteratively. So that would be, for instance, the Krylov space and T applied to the Krylov space. So a very nice survey on these subspace recycling iterative methods, at least in finite dimension, has been done by Sudhalter, De Stoller, and Misha Kilmer in this paper here, GAM-Mitteilung, volume 33 in 2020. So it's a very, very nice review on these methods. Okay, so some settings here. So we have the space U, and that would be the span of this U vectors, elements U1 up to UK. So that's our information that we have available where we think part of the solution belongs to. And U tilde equals just applying the operator T on this space, so on any elements of this space here. Later on, there's actually a small mistake. This U tilde is actually also called C, so that you calligraphic C, you don't get mixed up here. So that's just an error that I made when writing the slides here. Okay, so if we have these spaces U and U tilde, then we can form actually matrices U. So that's just the columns of the columns collected in this matrix here, this U1, U2 up to UK. So this is an element of the function space X power K. And the same here, C. So we just take the function C1, C2 up to CK from the space Y power K. So that's these kind of collection of vectors. Basically, it's in finite dimension, it would be just a matrix. And also we apply U to some element Z. Z is an element in RK, so that would be a vector here. And we actually define U applied to Z is simply the sum from 1 up to K. We multiply the numbers ZY with the functions UY. The same for C applied to Z, so we just sum up. So what else do we need? Well, we have this pair. This is actually X applied to U, and this is really a vector in RK. So this vector collects the inner products of X with U1 up to X inner product UK. And the same here for this matrix C. So basically it's just the vector, the inner products of Y with the rows of C, the columns of C. And also we define the bilinear mapping. So when we have M and L, which are two elements of X power K here, so then this ML is simply describes the matrix of all the pairs of inner products between elements of M and elements of L. So that's an RK times K matrix. So that's just for notation. Okay, so now what we actually need is some assumption on the operator T. So we assume first that the vectors ui in our collection of vectors where we actually collected for the augmentation, first they should be linear independent, which makes sense. You don't want to have in your space U vectors which are linear dependent. And also what we assume is that the operator T restricted to the subspace is invertible on its range. So that's, of course, an assumption which is not so easy to verify. But if, for instance, if it's injective, the operator is injective, then it's not a problem. In this case, if you now form the matrix CC here, then this matrix, which belongs to R K times K, this matrix is actually invertible. So continuously, it doesn't matter here, this word, so it's invertible. So you can actually invert this matrix. So for what comes now is we need actually projectors onto the space U and U tilde. So this U tilde now is here from now on called C here. And we call Q is the orthogonal projector onto the space C, and P is the orthogonal projector onto the space U. And these projectors, they can be characterized in terms of these operators that I introduced before. So we assume that U actually forms the basis of this xk, and that C is actually T applied to U, which is an element of yk. This is also the basis of C. And then we have that we can decompose, or that we can represent this projection onto the spaces U and V by these operations here. So basically we have a vector, we have here a matrix that we have to invert, and then we apply U again. So that's the projection. So having these functions here, U and Z defined before, we can really compute explicitly these projections by these formulas. Okay, so now we have these projections available. And then the next step is that we want to split the solution that we are looking for, the solution x dagger of our equation Tx equals y, in the part which belongs to U and the part that actually belongs to the orthogonal complement of U. So we have these two parts. And now we said xp dagger equals the projection of x, dagger. So the projection onto the space U. And by this formula up here, we know how that actually looks. So this is xp dagger. That's so to say the solution restricted onto the subspace U. Of course, whenever we have noisy data, y delta, this xp delta cannot be computed directly. But what we can compute is if we actually go back here, use this formula here and replace y by y delta. That's what we have done here. Then we get an xp delta and an yp by, we get actually by applying t to xp delta. So then we get yp. And what you can prove then first is that the approximation error between xp dagger and xp delta, so this element here, can be estimated as follows. So you have the norm of the difference is a factor times delta. So in contrast to regular or to normal inverse problems where you never get an approximation which is better or which is even O of delta, you always get O of delta power something which is smaller than 1. This part can be estimated by delta. So, and for the next step, we need to estimate the data error once you remove this yp defined up here from your true data. And there we need another assumption, namely that if we actually take the solution x dagger, apply the projector I minus p, then t and then q, that should be 0. So basically it means that if you take the solution, it doesn't mix with all the spaces. So in this case, we can still show that if we actually remove yp from y and yp delta from y delta, then this is still bounded by delta. Okay. And then we did another assumption. See, I used today a lot of assumption, basically that if we apply the adjoint of T to the subspace C, that should be perpendicular to I minus P applied to X dagger. This is, of course, that looks complicated, but it is always fulfilled if you actually assume, for instance, that you have chosen the subspace U, such that if you apply T star T to U, you're still back in a subspace of U. So when this holds, then this is always fulfilled. So is that a complicated or is it an easy assumption? That's not totally clear, but of course we have at least some easy cases where it's fulfilled. And the first one is, well, if you assume that that you actually put into U some of the eigenvalues or eigenvectors of the operator T, so just a few of them, then you always have that T star T applied to U is a subset of U, simply by the eigenvector equation that we have here. So that's easy. But also if T is an unitary operator, which means that the inner product of T with an element x1 with a T an element applied to an element x2 equals x1, x2 the inner products. If that holds for all x1, x2, then we also have that this condition 8 here is fulfilled. So it's not totally impossible to have this solution, to have this equation here fulfilled. Okay, so what is then augmented regularization? So we have so that's the algorithm here. So we have our data y delta that fulfills our error bound. We have chosen the finite dimensional subspace U and an arbitrary regularization method that we know that could be Landweber, it could be Tironov, together with a parameter choice rule alpha, depending on delta. So the first thing what we do is we compute xp delta according to the function, to the formula that we have seen before, and we said yp delta equals txp delta. So that can be done on the fly. That's just very easy. It's basically solving a finite dimensional, a low dimensional finite system. Then we set a new operator b, which is I minus q applied to t, and compute this xp delta hat here by applying an arbitrary regularization method to the data y delta minus yp delta. So that's the augmented data and the operator b. So, and finally, our reconstruction x delta, depending on the subspace U here and the regularization parameter, is simply the sum between this xp delta and this x hat p delta here. So these two elements here. And if I do that, well, what I can actually prove is that if for the solution x dagger of our equation and the chosen augmentation space, this original inequality holds, so this is, just go back to that, this this actually property holds, then the augmented regularization with data y delta, as described in our algorithm here, not algorithm 10, but algorithm 1, forms the regularization method. So it's as before, the properties of the regularization method that you have. The user regularization method here actually transformed to the augmented regularization. Okay, so for Landweber iteration or steepest descent, you can actually spell that out a little bit more, a little bit better. So the full augmented steepest descent approximation can be represented as follows. So the iterate xj plus 1 is described here. And if j equals 0, so that's the first iterate. So what you do is you take this xp delta, which you compute first, and then you add this term here, and then you continue your iteration. The main change is here that you have this projection always in there. Well, and you can actually do standard Landweber iteration, or you take the optimal step length, which is described here. Anyway, if you use this algorithm as it is described, then this is again a regularization method if you terminate the iteration with the discrepancy principle. Okay, so let's come to some numerics. And the first example is the standard Gaussian blurring model. So we consider here convolution problems. So the data is data Y is given as convolving the input X with a kernel K. And this K here is a Gaussian blurring kernel. We use a standard deviation sigma equals 6 in the blurring kernel. And yes, now the question is, of course, we want to reconstruct with an augmented Landweber method. We have first to find a strategy for creating the space U. And here what we simply did is the following. Well, we actually carried out two steepest descent iterations using the right-hand side Y here, but using different kernels. So we used actually different blurring operators with 5 different standard deviations. So we did that 5 times. So we did 5 times compute 2 steepest descent iterations, then we have 5 vectors, and these 5 vectors we used as the augmentation space. So of course, first we actually orthogonalize these 5 vectors, and then we put them into this space U here. Well, if we do that, that's just basically a play example here. We want to reconstruct these objects here. So that's just what you see in the data. And what you see on the right-hand side is what you would get as a best reconstruction by a classical steepest descent by applying that onto the blurred data. So if we actually look at the reconstruction that actually the augmented steepest descent method produced, then we see it's definitely not worse. But if you compare this row here with what we did before, you see it's a little bit better even. What is really astonishing, well, not astonishing, but we really can show is that these recycled methods, the subspace recycling approach, actually converge much faster. So you see here, that's the recycled steepest descent, no noise, that's with noise here. You see that this actually converges with fewer iterations here in the residual and here in the actually error. So it goes faster than the standard steepest descent method. Okay, so for the next 2 examples that I want to show you very shortly, that I have to step a little bit back and go to an adaptive optics problem here, which is related to the construction of the European extremely large telescope, which is currently on its way in Chile. It is about let's put it like here, that's the extremely large telescope, which will actually have a mirror of 39 meters in diameter. And my group actually participates in this construction of algorithms, or in the construction instruments for this ELT by providing some algorithms. And I just skipped that. So that's actually where the telescope will be located. I'm a little bit in a hurry here. So that's how it looks. These instruments are placed in the dome here, but I'm jumping a little bit to the mess here. Yes. Just what is the problem for the telescope? The image formation on the telescope is actually described by convolving the true image by a point spread function. And the point spread function is easily described as the Fourier transform of the characteristic function of the telescope. So that's kind of a donut or a circle with a hole in there. And the PSF is the Fourier transform here, it's the absolute value of the square. And what you see is the larger the telescope, you see that here compared to here, the larger the telescope, the more the PSF actually resembles a data distribution, which means you get almost the sharpest possible image of your object. Okay, so the problem, of course, is that you have a ground-based telescope. Also, the turbulence in the atmosphere plays a role, which means that the point spread function is affected by the turbulence in the atmosphere. So the point spread function is now characteristic function as we had before. and then an exponential here, which depends on the turbulence in the atmosphere. And what you see is that here on the left-hand side, the point spread function of the large telescope with atmosphere is not at all resembling a delta distribution anymore. And what we are using here is adaptive optics corrected imaging. So the point spread function after the adaptive optics correction looks at least a little bit more like a delta distribution. Okay, so adaptive optics, very fast here. I'm just stepping through that very fast. Is what you do is actually you have the light from the telescope. You have some kind of adaptive mirror where you can deform the shape of the mirror, and you have some kind of a wavefront sensor, and you use the light coming from a so-called guide star to reconstruct. So that's again an inverse problem, to reconstruct the shape of the incoming wavefronts from the light. And based on this reconstruction, you deform this mirror here in order to get a sharp image. So that's what is actually about adaptive optics. I'm not going much into details here because time is short. What I want to show you is a reconstruction for one of these wavefront sensors that we did for the so-called pyramid wavefront sensor, which you see here on the left-hand side. So a wave coming from space falls onto the top of this pyramidal prism that you see here, and then you get 4 images there, and out of these 4 images you form data as X as Y. So by just summing these intensities, these intensity distributions up in the right way, and that's your data. And the pyramid model, a linearized version of the pyramid sensor connecting the incoming wavefronts with the measurements is given here. So it's basically a classical transformation, an integral transformation, and the task would be a singular integral transformation. The task would be from this data to reconstruct phi. And also what I have to say is it has to be done very, very fast depending on the system. So you have for one reconstruction more or less than 1 milliseconds for the reconstruction. Okay, so the changes in the wavefronts are usually small from one time step to another. So we could actually use the previous time steps, the previous reconstruction, to form the space U here in our augmented regularization method. So, and we did that, and what we see here is that's basically the reconstruction quality. It's a kind of inverse, so we don't want to go to 0, we want to approach 1. If you look at the so-called Strehl ratio here, so the classical steepest descent method just has this curve here, so it goes after some time steps, converges to something like 0.7, but the augmented versions are, first they go much faster up, and then also they are have a much higher quality. So that works very well. Just one very short remark, you could also do that later on once you have already your image and you know the point spread function in order to deconvolution. And also that works very, very nice. If you use basically for your augmentation, the eigenvectors, the first couple of eigenvectors of your point spread function represented as a matrix from the point spread function without any turbulence in between, and that can be done beforehand. And if you do that, you really get, I just go there to the pictures here. If you actually, that is the original one. That's the one that you actually get, a blurred version. And if you use our approach, you get a very nice reconstruction of the original image. So what I've showed you basically in my talk is that by using the augmentation approach, you have 2 advances here. So the first one is that if you use your augmentation space properly, you get a better reconstruction quality for your problem at hand at one point. And the other one is you're usually faster in reconstruction. So that's the 2 benefits of that. And of course, the big mystery always is how you choose your augmentation space, but there, for instance, also approaches like learning these augmentation spaces could help in the future, and that's something we are looking into currently. So thanks for your attention, and sorry for stepping a little bit over time.
Okay, Professor Ramlau, thank you very much for your talk. And colleagues, well, are there any questions?
Yes, may I ask a question?
Yes, please.
Dear Ronnie, thank you very much for the very professional talk. And I would like to ask you about the connection between nowadays neural networks, tsunami. Everybody can use neural networks. What do you think about the probability, or is it possible to use neural networks in the regularization theory on deep learning and so on?
That's a very tricky question. You know that, of course. I mean, what people say is, well, it's very easy to use neural network, to use deep learning, and so on and so on. So I put some of my people in that direction. And the first observation is, no, it's not true. It's not true that it's easy to apply that. It's a lot of, using the right algorithms, tweaking everything. So it's not easier. So to put together a working neural network or a working deep learning approach is very, very complicated. That's the first point. So it's not like something that every dummy also can do. That's definitely not the case. And the second thing is, it always depends. It always depends on the kind of data that are available for training the network and what you want to reconstruct. So like, so we did once this example. If you train your network with tons of pictures of apples, and then you want to put in a peach for reconstruction or a walnut, nothing useful comes out. So the reconstruction is very much biased towards, of course, the learned structure. So what we are looking into it, what I see is really the thing that should be done is kind of hybrid data science, where you actually combine learned models and physical models in one instance. Like, just give you an example, in astrophysics, for instance, the astronomers quite often have an idea about a physical structure of what they are looking at, but this physical structure is not fully determined. There are some parameters missing and so on. So the idea would really be to use the data that is available and the physical model that is available, and together to optimize that in a hybrid learning approach, I would call it. So I think that's the future.
Thank you. I'm definitely on your side in this discussion. Thank you.
Well, colleagues, any questions? Professor Ramlau, I have a question. Could you please tell me, it is possible to apply your technique to investigate the convergence or to investigate the gradient descent method with momentum, something like a heavy ball method and so on?
I think whenever you have a reconstruction method, I think you can use this kind of approach, because what I showed is basically as an input, what you need is a reconstruction method, and you need a subspace where you think part of your solution might be located. And if these two ingredients are fulfilled, you can use that.
Okay. Thank you. Are there any questions? Well, if there are no questions, so thank you very much for your talk, Professor Ramlau. Thank you.
Thanks for having me.
Okay, thank you. Well, and the next talk is this is a joint work with Alasami and Daniel Lesnik and Nisan.
Yes, correct.
Okay,
Hello,
so could you please share your screen?
sure. Can you see my screen now?
Yes, please. That's okay.
My talk is concerned with the parameter determination problems in thermal wave by heat transfer. And this is the outline of my talk. So I'll discuss the mathematical formulation of the problem. Then I'll discuss solving the direct problem as well as solving the inverse problem. I'll give some examples as I go along. And if you are interested, you can read those papers, which have been published very recently. Now we are concerned with this model. It's used to model heat propagation in biological bodies, and it contains very important parameters, such as the blood perfusion rate, denoted by omega B, and also the heat generations, such as the metabolic heat generation and the spatial heating. This equation 1, has been derived to account for the finite speed of heat propagation present in biological tissues, which is a value in between 15 to 30 seconds. And this modification gives rise to this so-called Maxwell-Cattaneo equation, which connects the heat flux to the temperature gradient and also accounts for the delay in heat flux, denoted by tau. And by a first order approximation, we obtain this relation, connecting, as I said, the heat flux to the temperature gradient. Now it's interesting to note that a zero flux boundary condition maintains as the normal, as the zero Newman boundary condition. However, if we prescribe an n0 flux boundary condition, this doesn't hold as in terms of the normal derivative of T. As for the Robin boundary condition, we have the generalized Newton's law given by equation 3. And from this equation and the Nanforet's law of heat conduction, we can obtain this usual Robin boundary condition given by equation 4. Now, the problem is to solve the thermal wave model in each layer. So we assume the tissue is one-dimensional and multi-layered. So we have J layers. And the idea is to solve, or the problem is to solve the model in each layer. Of course, we have to account for additional conditions at the interfaces of the tissues, right? And those are given by the continuity of the temperature, given by equation 6, and the continuity of the heat flux, given here. And based on this condition, we can take the time derivative and multiply both sides by tau, sum the left-hand sides and the right-hand sides, and use the Nanforet's law of heat conduction to connect the equation in the heat flux to for the temperature. So it's easier to work in T with equations involving T rather than Q. But we have assumed a condition or an additional assumption, which is this assumption. We assume the relaxation time is constant over each layer of the tissue. Now, we assume the initial temperature is uniform, so it's constant, and we assume the heating process is initiated from rest. So we have those conditions, those initial conditions. As for the boundary conditions, we have convection at the tissue skin. So we have this Robin boundary condition. However, for the other end of the tissue, the most inner wall, we have two conditions. Either we prescribe the temperature, or either we have insulated boundary condition. And those conditions are used in the literature. If you look in bioheat transfer, you can see authors used either this one or this one. So now we have a complete description of the model. We can say dimensionalize it using those dimensionless scaling, right, to obtain this dimensionless model given by equation 11. And those are the corresponding conditions, all in dimensionless form. And those are the dimensionless parameters involving or that involve the dimensional properties. And from this condition or from those equations, the idea or what we want to solve the inverse problem of retrieving the heat capacity of each layer of the tissue, as well as the thermal conductivity and the blood perfusion rate. So we solve for those from those algebraic equations. And now we have this model, we can develop a direct solver, and the easiest way is to use finite difference method. And we choose the Grant-Nicholson scheme because it's convergent and unconditionally stable, and also second order accurate in space and time. And those properties have been proven in this reference by Sun et al. And now we can investigate some physical problems available in the literature. So the tissues might have 3 layers, 4 layers, or even 7 layers. And in the next slides, we will investigate 3-layer and 4-layer tissues. So in this physical example, as I said, we investigate or we solve a problem concerning three-layered skin tissue radiated or subjected to laser according to equation 17. And as you can see, there is I naught, which is the intensity of the heat, and also it involves what they call it. There is radiation in the, the radiation stops at an instant of time given by Tp. So we have this Heaviside function approximated by equation 18. And also we assume there is no metabolic heat in the tissue. So we took a QM equal 0. And the properties of the tissue are taken from this reference, from table 3 from this reference. We also took the remaining parameters as you can see in the slide. We also took the relaxation time to be 20 seconds, which is characteristic to biological bodies. So in other engineering materials like iron or similar materials, we have tau very, very small, extremely small, close to 0. However, for the biological bodies, as I mentioned before, we have this delay in heat flux. And those are the properties that we want to retrieve later on when we talk about the inverse problem. And we have, as I said, 3-layer tissue, epidermis, dermis, hypodermis. And so now we solve the dimensionless model using the above quantities or parameters given in dimensionless form, as you can see. And those are the, as you can see, the solution is convergent. Those are just realizations of the solution at the boundary of the tissue. So we have this, in this example, we investigated the second condition given as the insulated heat flux at the most inner wall for the downstream end. So we have theta 1, theta 3. And as you can see, the solution is negative. And this is because of the model. The model is hyperbolic type, and it contains the derivative of the source. And this acts as a sink rather than a source for this hyperbolic model. And this behavior has been highlighted in the literature before. In this problem, in the second problem, we investigate the same tissue. However, we investigate the case where we prescribe the temperature at the downstream end. So the properties are all the same, but the boundary condition is different. And we solve the dimensionless model using those parameters, and we obtain the solution. So the solution, as you can see, the solution to the direct problem is convergent as we refine the step. In this example, we investigate, the third example, we investigate a 4-layered thigh tissue stratified into skin, fat, muscle, and bone, and irradiated by this electromagnetic aggression. And you can notice the exponent of the exponential function. There is a number which is 0.01 that corresponds to the probe position if you have a tumor. So it's like heating the tumor to eradicate it. And the tumor is in this position, for instance. And we also assume there is no metabolic generation, and we solved the direct problem with those properties. And again, tau is taken equal 20 seconds. And those are the properties that we want to retrieve later on. Or those, as you can see, we have 4-layered tissue. And we solve the dimensionless model with those parameters to obtain the temperature. And as you can see, the solution is convergent when we refine the step, or as we refine the step. Now I'll mention, or I'll describe the inverse problem that we want to solve, as well as how to solve it. Then I'll solve the inverse problem for the 3 examples that I described or explained. Now the inverse problem is to find those properties given by the thermal conductivity, heat capacity, and the blood perfusion rate from the temperature, from observation of the temperature internally or at the boundary, depending on the problem. And the observation or the measurement are simulated from the forward model. And when solving the inverse problem, we use different mesh size so that we avoid committing an inverse crime. And we also invert for noisy data generated by adding random noise sampled from Gaussian normal distribution with 0 mean and standard deviation given as such, where P is the level of noise or the percentage of noise. Now we recover the dimensionless parameters given by A1, A2, A4 for each layer, and those parameters connect or are connected to the dimensional parameters that we want to retrieve. And the idea is to minimize this misfit function, right? Where theta is the measurement and theta C are the computed temperature found from the direct or from the forward model for a given vector A. And we used MATLAB built-in solver to minimize equation 25. So in this example, we minimize this objective function. It's a bit different. It's weighted objective function, and we measured the temperature at the boundary. So this example corresponds to example 1 of the direct problem. And because we prescribed convective boundary condition and adiabatic boundary condition, we can measure the temperature at the boundary. So we took it as measurements. And this is the objective function as a function of the number of iterations for noiseless data and noisy data. As you can see, it converged. And those are the minimizers of the minimization problem. Those are the solution of the minimization problem. As you can see, the relative error is small. And those are the solution for the dimensional parameters. Again, the relative errors are small. As I mentioned, this example has considered an adiabatic boundary condition, which allowed the temperature to be taken at the downstream end. However, if we prescribe a tertiary boundary condition, we might need additional measurements, not just the tissue skin. And those measurements are of the form of internal measurements in the epidermis, dermis, or hypodermis. And this case is investigated in the next slide, as you will see. So again, we solve the same problems. The difference is just the boundary condition, and we investigate 4 cases. So I is the number of measurements. So we investigate for I equal 1, 2, 3, 4, and we see how the solution to the minimization problem corresponds to the number of measurements. And this is the objective function G as a function of the number of iterations. As you can see, G for I equal 3 and I equal 4 is similar, right? And while for the other cases, it's very big compared to this. So based on this, we choose the solution for I equal 3 as the desired, or as the solution to the inverse problem, as the desired physical solution, right? And those are the minimizers to the objective function for I equal 1, 2, and 3. As you can see, some relative errors are big. So we don't choose those solutions, except for I equal 4, but we don't also choose this. It's nice to reconstruct using minimal or as minimum as possible, as minimum measurements. Now, those are the dimensionless parameters for I equal 3. And as you can see, the relative errors are small for noiseless and noisy data, and also the dimensional parameters. As you can see, the relative error is small. Now, this third example corresponds to the 4-layered thigh tissue, and we want to retrieve, as I mentioned before, those properties, and we investigate 4 measurements. The measurements are supplied at the tissue surface and also internally at the midpoint of each layer. It's similar to the example 2. We have 4 measurements, and the measurements are internally at the midpoint. And those are the dimensionless positions of the measurements. And this is the objective function as a function of the number of iteration. As you can see, we have many minimizers to the objective function for each case of I equal 1, 2, 3, and 4. And for I equal 4, the objective function attains a very minimum value. So based on this behavior, we pick the solution for I equal 4 as the desired solution. And those are the minimizers for I equal 1, 2, and 3. As you can see, some relative errors are big. Right, so we have this and this are very big. However, for I equal 4, we have the minimizers as the solution to the inverse problem. So we took those this solution as the solution to the inverse problem for I equal for noiseless and noisy data as well. And those are the dimensional parameters. Again, found from the dimensionless conditions from the non-dimensionalization. And this is pretty much my talk. So in conclusion, we have considered retrieving the properties or the thermophysical properties of multi-layered tissues. And for the case of an adiabatic wall or also known as insulated boundary condition, we have found boundary conditions, non-intrusive measurements are sufficient to retrieve the properties. However, for a tertiary boundary condition, we required additional measurements internally to retrieve the unknowns. And those are, I mean, in the future, we plan to extend and invert the thermophysical properties for more general or more involved or more used model, like the dual phase lag model. We also, in this work, we accounted for constant properties, but in the future, we might extend it to account for temperature-dependent properties. We also plan to retrieve the shape of a tumor in irregular tissues. And in this case, we need another direct solver, not a finite difference method, because this tissue is irregular. And we might invert data from experiments. And those are the references. Any question?
Well, thank you for your talk, and colleagues. Any questions? Well, could you please tell me where can you find the thermal or diffusion parameters of human tissues? Because I know that it's really a problem when we solve the acoustical tomography, so it's very hard to find the acoustic parameters of the human tissue.
Yeah, I talked from the literature. There are some studies, some experimental studies, which showed those properties. So I only took them from the literature. I didn't do any experiments.
Okay.
But it's possible to do some measurements, I think.
Okay, thank you. So any other questions? Well, if there are no questions, so thank you very much for your talk. And this was last talk for today, and we will continue tomorrow. And we have the following program for today, for tomorrow. So this is we have a all day working day, so please connect to Zoom and participate in the conference. Well, so thank you very much. Thank you for participation, and we are looking forward to see you tomorrow.
Thank you. See you tomorrow. Good night, everybody.
Thank you.
Tomorrow morning.
До свидания, Владимир Васильевич. Да.
See you tomorrow.
See you tomorrow. Bye-bye.
Всем успехов. Спасибо за соучастие. До свидания.
Спасибо. До свидания.